A signal just moved through a lab outside Beijing at a speed that shouldn't be possible yet. Somewhere in Nanjing, a stretch of highway is quietly running a wireless network that doesn't officially exist. A government ministry just approved a slice of spectrum that most of the world hasn't even started fighting over. And in Shanghai, engineers are streaming 86 channels of 8K video through a single fiber and wireless system at once without breaking a sweat. None of this is science fiction. None of it is a decade away. It is happening right now in 2026, and by the time most people even understand what 5G actually did for them, China is already building the thing that replaces it. What you're about to hear is not a prediction. It's a progress report on a technology race that most of the planet doesn't know has already started. This isn't fringe speculation or a state media fantasy. In February 2026, a research team from Peking University, working alongside the Pengcheng Laboratory, Shanghai Tech University, and the National Optoelectronics Innovation Center, published a peer-reviewed study in the journal Nature, one of the most rigorously vetted scientific publications on Earth. The paper wasn't about slogans or 5-year plans. It was about hard, testable numbers, a new integrated communication system that fuses optical fiber and wireless transmission into a single architecture, and does it faster than anyone has ever recorded. Wang Xingjun, Vice Dean of the School of Electronics at Peking University, and one of the paper's corresponding authors, has spent years building a publication record inside journals like Nature Photonics and Light, Science and Applications. This is not a team chasing headlines. This is a team that has been quietly laying the groundwork for this exact moment for the better part of a decade. To understand why this matters, you need a simple picture of what 6G is actually trying to fix. Think about the difference between a single-lane road and a 12-lane highway during rush hour. 5G is that single-lane road. It works, it moves traffic, but the moment you add self-driving cars, remote surgery robots, citywide sensor networks, and millions of AI devices all trying to talk to each other at once, that road becomes a parking lot. 6G is the 12-lane highway, but it's more than that. It's a highway that can also sense the weather, redirect itself in real time, and let a car and a traffic light have an actual two-way conversation instead of just broadcasting blindly. That's the leap being engineered right now. And here's the number that puts it in perspective, stacked 2 ways so it actually lands. The new fiber wireless system recorded a single-channel wireless transmission speed of 400 gigabits per second, alongside 512 gigabits per second over fiber. To compare that to something familiar, a typical home 5G connection today tops out somewhere in the range of 1 to 2 gigabits per second on a good day. That means this lab result is running at roughly 200 to 400 times the speed most people experience on their phones right now. Now compare it to time instead of speed. Downloading a full high-definition movie on an average current mobile connection might take several minutes. At these lab speeds, that same file transfers in a fraction of a second, faster than you could finish reading this sentence. Here's where it gets interesting, because a lab result and a real network are two very different things, and the story doesn't stop at the Nature paper. The core problem the Peking University team solved wasn't just raw speed. It was what researchers call the bandwidth gap, the long-standing mismatch between how fiber optic cables carry data and how wireless signals carry data. For decades, these two systems have essentially spoken different languages, forcing network engineers to build clunky translation layers between them every time information moved from a wired backbone to a wireless tower. Wang Xingjun's team built what they describe as an all-optical dual-mode architecture, a system where the same underlying hardware can shift between fiber and wireless transmission without that awkward translation step. In their large-scale simulation, the team modeled a real 6G user access scenario and successfully streamed real-time 8K video across 86 channels simultaneously, hitting a combined bandwidth more than 10 times higher than what current 5G networks are capable of. 86 channels of 8K video running at once without the system buckling. That is not a small technical footnote. That is a demonstration that this architecture can survive contact with something resembling real-world demand, not just a sterile lab bench test. And the researchers didn't stop at raw throughput. Reporting on the same system, the team also highlighted its performance on 3 practical measures that rarely make it into headlines but matter enormously to any engineer deciding whether to actually build something at scale: energy consumption, cost, and scalability. A system that can move this much data but burns through power at an unsustainable rate, or costs a fortune per unit to manufacture, is a curiosity, not infrastructure. The fact that this one was described as competitive on all 3 fronts, on top of the speed record, is what separates a headline-grabbing demo from something a national telecom operator might actually consider deploying across thousands of base stations. Now, before this starts to sound like one lucky paper from one university, it's worth pausing to recap what's been established so far, because the next part builds directly on it. A peer-reviewed, Nature-published system has already broken wireless and fiber speed records. It's already been stress-tested in a simulated 6G environment with dozens of channels running at once. And it was built specifically with next-generation networks and AI data centers in mind, not as an academic curiosity, but as functioning infrastructure aimed at a real deployment target. So the question becomes obvious. If the technology exists in a lab, how far is it from existing in the real world? That's where the story shifts from Beijing University labs out into actual Chinese soil. In April 2026, Purple Mountain Laboratories, a state-backed research institute based in Nanjing, quietly flipped the switch on what it calls China's first pre-6G outdoor trial network. This is not a simulation. This is not a paper. This is a physical stretch of infrastructure, layered directly on top of existing 5G networks, running experimental 6G technologies in an actual outdoor environment where real signals face real interference, real weather, and real distance. The purpose of this trial network is deliberately different from the Peking University breakthrough. Where the Nature paper proved a concept could work in principle, Purple Mountain Laboratories is testing whether an entire system, end-to-end, can function reliably outside a controlled lab. Reported capabilities from the trial include high bandwidth, long-distance coverage, deterministic low latency, and built-in sensing and AI functions woven directly into the network itself, rather than bolted on afterward. And the use cases being tested aren't abstract. Engineers are running trials for low-altitude drone inspection, industrial manufacturing automation, embodied intelligence, essentially physical robots that need instant network feedback to move safely, and holographic communications, the kind of three-dimensional video calling that's been promised in tech demos for years, but has never had a network fast enough to actually carry it. Each of these use cases has its own reason for needing something beyond 5G. A drone inspecting power lines or pipelines from a low altitude needs a network that doesn't drop out the moment it crosses from one coverage cell into another, because a dropped connection at altitude isn't just an inconvenience. It can mean a lost aircraft, a factory floor running embodied intelligence, meaning physical robotic arms and mobile robots making split-second movement decisions, needs latency low enough that the gap between a sensor detecting a problem and a machine reacting to it is effectively unnoticeable. And holographic communication needs enough simultaneous bandwidth to carry a three-dimensional volumetric image of a person in real time, which is a dramatically heavier load than a flat video call. None of these are hypothetical wish list items. They're the specific stress tests Purple Mountain Laboratories built its outdoor trial network to run. Here's the part that connects everything together. None of this is happening in isolation, and it isn't the work of one lab chasing prestige. China's Ministry of Industry and Information Technology, known as MIIT, has been running a coordinated national strategy since at least 2019, when the IMT 2030, or 6G, promotion group was established specifically to align telecom companies, universities, and government agencies around a single roadmap. According to Du Ying, Deputy Director of the Wireless and Mobile Communications Institute at the China Academy of Information and Communications Technology, China completed its first phase of national 6G key technology testing between 2022 and 2025, and in that window alone accumulated more than 300 core technologies. 300 core technologies. That is not a handful of promising experiments. That is an entire technological ecosystem being assembled piece by piece on a timeline with a government body tracking the progress. If you enjoy watching a country execute a decade-long plan with this kind of precision, this is probably a good moment to hit subscribe. Because the next layer of this story gets even stranger, and you don't want to miss where it goes. In July 2026, MIIT confirmed it was accelerating into the second phase of national 6G trials. This followed the completion of Phase 1, the approval of experimental spectrum in the 6 GHz frequency range, a critical resource that different countries are quietly racing to lock down before international standards get finalized, and the launch of coordinated pilot programs across multiple provinces. On June 4, 2026, MIIT launched what it called a Ministry-Province Collaborative 6G Pilot Initiative, inviting participating provinces and municipalities to each select between 1 and 3 development areas based on their existing research strengths. This is the part that separates China's approach from a lot of other national tech pushes. Instead of centralizing everything in one city or one lab, the strategy spreads specialized development across the country. Regions with strong industrial bases work on industrial automation use cases, while regions with strong academic clusters work on core physics and signal processing. It's less like building one skyscraper and more like constructing an entire city grid, one district at a time, all wired to the same blueprint. So what is 6G actually supposed to do differently once all these pieces come together? According to Xiao Chunju, director of the Future Research Lab at the China Mobile Research Institute, 6G is designed to deeply integrate communication, sensing, computing, and artificial intelligence into a single unified system, with the goal of achieving what's described as ubiquitous coverage across space, air, and ground. That last phrase matters more than it might sound at first. Current mobile networks are essentially ground-based. Towers, cables, data centers, all rooted to the Earth. A network that spans space, air, and ground means satellites, drones, and terrestrial towers all working as one continuous system, rather than three separate networks that occasionally hand off signals to each other. Picture a rural area with no cell, towers for miles, or a cargo ship in the middle of the ocean, or a drone flying at an altitude where ground towers simply can't reach it. In a space-air-ground integrated network, that drone, that ship, and that remote village would theoretically all sit on the exact same seamless network as someone standing in the middle of Beijing. There's also a question worth sitting with here. What happens to global supply chains, disaster response, and military logistics once distance stops being the limiting factor for high-speed connectivity? That's not a small shift. That's a fundamentally different relationship between geography and connection. To be clear, nobody's claiming this already exists as a working, unified system today. What's being described is the design target that's shaping how spectrum, satellites, and ground infrastructure are being planned together from the outset, rather than as three separate industries that occasionally interconnect after the fact. That distinction, designing for integration from day one instead of bolting systems together later, is a big part of why Chinese planners keep describing 6G as a fundamentally different kind of network rather than simply a faster version of 5G. Now, here's the part that connects back to why the speed numbers matter so much in the first place. All of this, the sensing, the AI integration, the space-air-ground coverage, requires an enormous amount of bandwidth moving with almost no delay, which is exactly the bottleneck the Peking University fiber wireless system was built to solve, and exactly what the Purple Mountain Labs trial network is currently testing in the real world. These aren't separate stories. They're layers of the same rollout, built by different teams, tested at different stages, all converging toward the same national target. China Mobile, China Telecom, and China Unicom, the country's three dominant network operators, are reportedly coordinating their research activities specifically to make sure whatever emerges from these trials is compatible across networks, rather than fractured into competing, incompatible systems, a mistake that slowed adoption in earlier generations of wireless technology. It does not guarantee success, but it does mean the pieces are being deliberately fitted together, not left to compete against each other by accident. There's a separate thread in this story that deserves its own moment because it shows just how far the underlying research has advanced beyond a single speed record. In work associated with Wang Xingjun's group at Peking University, alongside collaborators including Xu Haowen and Wang Chung at the City University of Hong Kong, researchers reported achieving what they describe as adaptive, full-band, high-speed wireless communication using an optoelectronic fusion approach, a system capable of supporting multiple generations of wireless standards from older 2G-era signals all the way up through 6G on a single unified hardware platform. That changed something important. For decades, upgrading a wireless network generation has meant physically installing new equipment, new towers, new base station hardware, because each generation of wireless technology has typically needed its own dedicated systems. A platform that can flexibly support 2G through 6G on the same hardware would mean network operators could theoretically upgrade capability through software and calibration, rather than tearing out and replacing physical infrastructure across an entire country. That is the kind of unglamorous engineering detail that rarely makes headlines, but it's often the difference between a technology that stays in a lab forever and one that actually gets deployed at national scale within a realistic budget. If you've made it this far, you've now got the full shape of what's being built. A record-breaking, peer-reviewed core system, a live outdoor trial network layering 6G capability on top of existing 5G infrastructure, a coordinated national ministry accelerating phase 2 of testing with dedicated spectrum, 3 major carriers aligning their research, and a hardware approach that could make future upgrades dramatically cheaper and faster to deploy. In the next part of this, it's worth pausing on what all of this is not, because that honesty is exactly what separates a real technology story from a hype cycle. Here's what needs to be said plainly, because it's the part that often gets skipped in coverage of stories like this one. Here is no finalized global 6G standard yet from China or anyone else. The International Telecommunication Union and various regional standards bodies are still in the process of defining what 6G officially requires. And until that process concludes, no country can claim to have deployed a true standardized 6G network because the target itself is still being drawn. What exists today, as of mid-2026, is a set of individually impressive but still fragmented pieces, laboratory speed records, simulated stress tests, and one physical outdoor trial network that remains explicitly experimental and layered on top of existing 5G rather than replacing it. Douying's own timeline reflects this reality directly, projecting commercial 6G services around 2030 at the earliest, with large-scale deployment not expected until roughly 2035. That is not next year. IT already deck. Hat is not even close to next year. It's important to separate what has been proven at the level of individual components, real record-breaking transmission speeds, a real functioning trial network, real coordinated spectrum allocation, from what has not yet been proven, which is a complete, standardized, nationwide 6G network actually carrying commercial traffic for ordinary people. The individual pieces are genuinely remarkable and independently verified. The full assembled system, running at national scale in everyday life, does not exist yet, anywhere in the world, and won't for years. It's also worth noting that China is not the only country running this race. Standards bodies, research consortiums, and telecom companies in the United States, the European Union, South Korea, and Japan are all pursuing their own 6G research programs in parallel, and which countries' specific technical approaches ultimately get folded into the eventual global standard is genuinely still an open question, not a foregone conclusion. What can be said with confidence, based on the published record, is that China's programs are moving with unusual coordination and speed. What can't be said yet is that China has already won a race that, by definition, doesn't have a finish line drawn on the track. It's also worth being honest about the geopolitical undercurrent here, because it shapes why the story gets so much attention in the first place. China's aggressive push into 6G research is widely understood, including by Chinese officials themselves, as a strategic response to the difficulties the country faced during the 5G era, when geopolitical restrictions and trade barriers slowed the international rollout of Chinese telecom equipment despite the underlying technology often being competitive. Accumulating patents early, coordinating research nationally, and pushing hard on foundational science are all moves clearly aimed at avoiding a repeat of that experience. That context doesn't make the underlying physics or engineering any less real, but it does mean some of the framing around this race, from every country involved, not just China, carries strategic motivation, alongside scientific substance. Recognizing that doesn't diminish the achievement. It just means watching the next few years with clear eyes rather than pure hype. So where does that leave things? A country most people associate with manufacturing and mobile apps has quietly become one of the 2 or 3 places on Earth actually capable of setting the terms for what wireless connectivity looks like for the next generation. Not through a single, dramatic announcement, but through a peer-reviewed paper here, an outdoor trial network there, a spectrum allocation, a ministry roadmap, 3 telecom giants aligning behind the scenes. It's less a single explosion and more a slow, deliberate tightening of a very large machine, bolt by bolt, lab by lab, province by province. And if the timeline holds, by the time most people are just getting comfortable with what their 5G phone can do, the infrastructure to make that phone feel ancient will already be sitting there, tested, refined, and waiting for the switch to flip. The single-lane road doesn't get replaced overnight. It gets quietly paved over, 12 lanes at a time, while most of the traffic on it has no idea construction has already started underneath them. Think back to that lab outside Beijing, that quiet stretch of highway in Nanjing. That spectrum allocation most people will never hear about. None of it looks dramatic from the outside. No sirens, no launch event, no countdown clock. But that's exactly how the biggest infrastructure shifts in history tend to arrive. Not with a bang, but with a paper published on a Wednesday and a trial network switched on in April that almost nobody outside the industry noticed. Tell me in the comments which detail actually surprised you more, the 512 gigabit fiber speed record from Peking University, or the fact that a live outdoor 6G trial network is already running in Nanjing right now,